Good evening, everybody. It's a real pleasure to see so many people for the first lecture, memorial lecture for Steve Weinberg. I had the honor and the privilege about 38 years ago to be hired by Steve. And what I noticed very early on and over the years, that he basically had two loves. One was his family, his wife Louise, his daughter Elizabeth, and later on his granddaughter Gabby. And they were very important to him. The other love he had was physics. And what was absolutely remarkable about Steve is that he had a knack of knowing what were the important problems. Not only did he know what the important problems were, but he knew which one was solvable. And he did solve several of them. What was awesome and awe-inspiring to me is the way when he started working on a problem, how focused he was. Nothing else mattered. Nothing in the world existed besides his family, obviously. He was focused on this problem, and no stones would be left unturned to understand the problem. He would look at this problem from all possible sides until he was satisfied, and then he would in general solve this problem in its most general way, which some of us never get to do. So that was something that was inspiring. The other thing, as you know, obviously in the few minutes I have, I cannot tell you many things about him, but you know that he wrote a bunch of technical books as well as popular books. And here is a little secret. I was educated at Université Libre de Bruxelles. And my education was sorely lacking. And I remember as a first postdoc at CERN, I would hear about the temperature of the universe. And I said, what the hell are they talking about? It's 20 degrees Celsius in this room. It's way cooler up high in the atmosphere. What the hell are they talking about? And I was too shy to ask my colleagues at CERN, what is he talking about? And then I discovered this little book called The First 3 Minutes. And I said, that's what they mean. And then through this book, I really fell in love with cosmology, did quite a bit of work in cosmology. So Steve was a giant. He's leaving, by his departure, a tremendous hole in the world of science. I miss him. I miss him terribly. I remember in the early days when he not the assistants or anybody else, would organize the informal seminars we had. We used to call them brown bag lunches. And they were in his room, in his office. The office was full, packed with students, packed with postdocs, packed with professors, up to the corridor. Didn't last long because there were too many people, but there was an excitement there. So, I mean, I have fond memories of all these years, and I miss him. I miss him terribly. And I wish I had the opportunity to tell him how much I loved him for the human being he was. So that's it for me. Thank you.
Good afternoon. I am Pablo Laguna. I'm the chair of the Department of Physics here at UT. And I want to welcome you to the inaugural memorial lecture in honor of Steven Weinberg. My colleague, Professor Katie Fries, was scheduled to introduce our speaker today, but unfortunately, she's not feeling well. I wish Katie a prompt recovery, and I take the opportunity to thank her for all the work on leading the organization of today's event. Our speaker today is Professor Frank Wilczek. Frank is the Herman Feshbach Professor of Physics at MIT, founding director of the T.D. Lee Institute and chief scientist at the Wilczek Quantum Center in Shanghai. He's also a distinguished professor at Arizona State University and a full professor at Stockholm University. It is very appropriate for Frank to deliver today's inaugural Weinberg Memorial Lecture. Frank and Steven Weinberg share broad interests in wide topics in physics, from seminal contributions to particle physics, cosmology, astrophysics, and condensed matter physics. Frank has received many, many awards for his groundbreaking work. Among them, he has a MacArthur Fellow, member of the National Academy of Science, the Lorentz Medal, a Littlefield Prize of the American Physical Society. And in 2004, Frank, along with David Gross and David Polisarch, was awarded the Nobel Prize in Physics for the discovery of asymptotic freedom in the theory of the strong interactions. Please join me welcoming Professor Frank Wilczek.
Well, it's an honor and a privilege to be giving this lecture. I'd like to start with a kind of personal picture. This was taken at Austin a couple of years ago. Vincent Liu, to explain what Hi Vincent is about, Vincent Liu was a student of Professor Weinberg's who became my postdoc, Steve and I and my wife Betsy were had dinner, and somehow the idea came up that we should send a note to Vincent. And Steve was so enthusiastic about this idea. He just couldn't be restrained until we took the picture. And this is the picture. And to me, this is a real treasure. It recalls very happy times, and also, to me, really captures something of Steve's jovial and generous spirit. So today I'd like to talk about quasi-particles and quasi-worlds. This is a way of talking about field theory, effective field theory, quantum field theory, things that were central to Steve Weinberg's work and mine and the work of all modern physicists, really. I think to convey the spirit of it to the public, this terminology of quasi-particles and quasi-worlds is very appropriate. And it also, I hope, for physicists will suggest some new points of view. It's been very fruitful for me. So in this talk, I will, first of all, tell you what quasi-particles are, and then what quasi-worlds are. Quasi-worlds are making their debut at this lecture. Then I'll talk about quasi-particles and quasi-worlds as at today's frontiers of research, sort of two case studies I'll describe briefly, breaking areas of research and discovery in physics right now, Anions and Axions. Axions are a field in which Professor Weinberg had seminal contributions. And then finally, I'll discuss where it's going, quo vadis. Steve was very fond of Latin phrases, so I thought I'd also include that. So, quasi-particles. As with many topics in physics, the roots of this idea, which unify the concepts of space, or ether, if you like, and substance, go back to Albert Einstein. In 1905, Einstein introduced the concept of the photon, which is very famous, is really what he got the Nobel Prize for, officially. But in 1907, 2 years later, he predicted the existence of another kind of particle, much less well known, but I think equally profound and central to the story I'm telling today. That's the phonon. Well, what are these things? And what was the leap of imagination that led him from one to the other? In both cases, the new particles were inspired by problems in thermodynamics, That is, what happens when you heat things up. In one case, it was what happens when you heat up space itself, if you like, the so-called problem of black body radiation. What happens when you excite electric and magnetic fields to have a non-zero temperature. And on the other hand, the problem of vibrations of crystals, sort of a much more tangible kind of vibration. So the vibrations of ether are vibrations of electric and magnetic fields. That's how we describe light and other forms of electromagnetic radiation. The vibrations of silicon are, well, just what you think they are. You hammer on silicon and it vibrates. And what was discovered experimentally and was very puzzling for classical physics in both cases is that the predicted very, very abundant small, very jagged jiggles, so-called high-frequency modes, were not present at the predicted level. And what Einstein proposed is that that's because there's a minimum amplitude of vibrations. And in fact, that these vibrations have the character of units, quanta, he called them. And if you have less than the quantum, you get no vibration at all. And this is the way he resolved that problem for the black body radiation. And then he had the wit, the imagination to say that that should also apply to vibrations of matter, and predicted that the vibrations of matter would also have a particle character. There would be quanta of vibrations. These are called phonons and have become a very, very important topic in condensed matter physics. I should have said, of course, both predictions were correct. Another example of the quasi-particle concept that really is the making of the modern world, I would claim, is the story of holes. Now, these holes are not holes in space. They're not holes in the geometrical sense. They are holes in the distribution of electrons, either in space, in the so-called Dirac sea, or inside materials. This has a more complex history than the photon story. I would say that there were three key figures in this history. And remarkably enough, there's a nice picture of the three of them together. These were Paul Dirac, Wolfgang Pauli, and Rudolf Peierls. Pauli, I would say, elucidated the concept of holes inside atoms with his so-called Pauli exclusion principle. So when you take out, you have different energy levels inside atoms. If you take an electron out, it leaves an empty space that has a character of its own. And Dirac, in analyzing his relativistic wave equation, made use of the concept that space itself is full of an electron's, just like a giant atom that's full of electrons, and used Pauli's idea to explain why his equations worked. And then Peierls applied these ideas to the analysis of materials. And actually, they're easiest to explain in the context of materials, even though they were, in some ways, the hardest to work out and came last. So let me discuss it in that way. If you have a material that has, of course, electrons in it, what happens if you take an electron out? Well, it depends on the material, but in many materials, what happens is that the material readjusts. If you pluck it out, it may have to do some readjustment to get into a stable state, radiates away some energy. But what remains is a concentration of energy that's kind of reproducible once it's settled down, and can move, and has a kind of localized character of a particle. And that's what's called holes in condensed matter physics. So it's a hole in the distribution of electrons. And you can, you can produce a hole by injecting energy into your material, as I said, and making a hole, and then taking an electron out of where it should be so it can move around, and then you have both a hole left behind and, whoops, didn't know it. Is this? Yeah, okay. Then you have both the hole left behind that I described and the electron that you've plucked out. So you've created a hole particle pair. And if you apply the same idea to Dirac's C, you also get a hole particle pair, and the hole is what's called an anti-electron or a positron. In the case of doing that in the vacuum, the energy difference here is 2 times the mass of the electron times c squared. In the case of solids, it can be much, much less. So you can have holes that are much less costly to make than antiparticles. These ideas quickly got experimental confirmation. This is a picture of production of a pair, electrons, an electron and an anti-electron or a positron in empty space. A photon comes in here, deposits energy, and produces this pair. You can tell that they have opposite charge because they're bending in opposite directions in a magnetic field. If you do this inside materials, it's much cheaper, doesn't require so much energy, and then you can separate. You can produce lots of these guys, and you can separate them using an electric field that makes the positive guys want to go one way and the negative guys go another way. And in that way, you can convert light into usable electronic energy. And that is the hope of the world, to create an energy that's sustainable on a grand scale, farming the energy of the sun. That's using this process of quasi-pair production that came out of fundamental thinking about the nature of matter. You can also make holes chemically by putting in what's called a dopant, a material that's different from what it should be, so to speak, in a matrix of a solid. So here in silicon, if you substitute boron, which has valence of 3, should only have few, can't take up as many electrons, or whole. It should take up. You can have dopants that either take up or take away electrons from the other guys, and that way you can make chemically. You can make either extra electrons, so-called quasi-electrons, because their properties are modified inside the material, or holes. And this is the technology, making chemically particles that have a kind of existence, with stable existence within matter, that have either charge and are cheap to produce, and you can manipulate them. That's the way you make transistors and all the structures of modern life on the line. To illustrate further the idea that the properties of particles change into something potentially quite different inside materials, let me talk for a moment about quasi-photons. So photons in space have certain properties, but photons inside materials, if you think of the materials as worlds of their own, the photons inside can have quite different properties than the photons on the outside. deserve to be called quasi-photons. A striking example of that is that the modern understanding of the phenomenon of superconductivity is that a superconductor is a material in which photons have acquired a non-zero mass. Neither more nor less. And a striking signature of superconductivity, in some ways the defining property, is the so-called Meissner effect, which is precisely the mismatch between what a photon wants to be in empty space and what it has to be if it gets inside the material. Because of this effect, when a material becomes superconducting, when you lower its temperature through the transition temperature, the photons that used to be happy penetrating through can no longer do it. They don't have enough oomph, enough energy, enough mass, and so the magnetic field gets excluded. So now let's move on to quasi-worlds. The first step is to think of the world as a material. This was an innovation, I would say, of 19th century physics. Newtonian physics imagined a void, that space was a void, just sort of a stage on which the characters of matter acted out their parts. Newton himself didn't like that. He thought it was not appropriate, but that's what his theories pointed to, and they were very successful, so he was stuck with it. However, in the 19th century, when people started to think not only about mechanics and the laws of gravitation following Newton, but electromagnetism, they discovered that electric and magnetic fields had kind of a life of their own, and that they filled space, and that the laws could be most simply formulated in terms of these space-filling entities, these fields. Maxwell was the great hero of this story. He discovered the equations, and the way he discovered the equations was very interesting. In order to get a model that was consistent with the existing experiments, but also with the general principles of how energy and momentum should flow, the general principles, he wanted to make a model that embodied the electric and magnetic phenomena as known in his time, but also satisfied the general consistency conditions. So he made a model which had circulating currents and vortices, and well, the details are very ingenious, incredibly ingenious actually, but obsolete. And Maxwell himself threw away this model, having, however, found a consistent set of equations based on worrying about making a model of a mechanical model of the flows of electric and magnetic radiation. And he was extraordinarily delighted about this discovery. I'm just going to read this because I love it. The vast interplanetary and interstellar regions will no longer be regarded as waste places in the universe, which the Creator has not seen fit to fill with the symbols of the manifold order of his kingdom. We shall find them to be already full of this wonderful medium, so full that no human power can remove it from the smallest portion of space or produce the slightest flaw in its infinite continuity. Wow. Okay. And more refined theories of gravity, Einstein's general relativity, made space and space-time into a material as well, a material in a very tangible sense that it can bend and vibrate. And the bending is responsible for gravitational forces in this new understanding of what gravity is. I think Newton would have been very happy with this picture, by the way. These ideas were perhaps most dramatically confirmed recently in the observation of gravitational waves by the LIGO interferometer, where two merging black holes set off ripples in space-time, tiny ripples that were observed here on Earth. The other forces of nature, the other fundamental forces, the other two that we know about the most right now, the strong and weak forces, are based on very similar principles to those theories of space-filling fields, especially close to the Maxwell theory, but also conceptually related to general relativity. And so we can ask similar questions about not what is black body radiation for electromagnetism, but what's the analog of black body radiation for the other stuff? That's what should have been filling the early universe, which is, according to Big Bang theory, a very hot, dense place with plenty of energy. So you could produce pairs of all the particles that exist, and that medium, once it comes into equilibrium, is what makes space early in its history. And you can also investigate this experimentally by producing, to be sure, only in a small volume and for a brief time, the same kind of energy concentrations, and seeing if the predictions of our theory really work. And this is what's done at what's called relativistic heavy ion collisions. So I hope I've convinced you with these brief indications that it's been very fruitful to think, or it's kind of forced on us to think of the world as a material. We can also think of materials as worlds. The mind tools that were developed to describe the world's fundamental interactions, field theory and its quantum field theory, can be used more widely. And in particular, they can be used to model and to imagine quasi-worlds. I always think here of something that Richard Feynman, another of my heroes, said. He said that physics requires imagination, but imagination in a straitjacket. This is the straitjacket. This is the straitjacket that we've come to know and love, to make consistent models that embody the basic principles of quantum mechanics and symmetry, and these are called the effective field theories. And so you can design worlds that are consistent with these principles, and then ask people to see if they can create those worlds. Those are the quasi-worlds. So going back to this figure, to illustrate, to emphasize, and maybe the fact that we think of space as matter and matter as space, that's just two different axes on this phase diagram of extreme matter. When you have extreme temperature, but low densities of matter, that's on this axis. When you have extreme density, but relatively low temperature, that's on this axis. But we think of it all together, and experiments can go in different directions and try to explore the whole range of possibilities in between. And there are very interesting things for physicists that happen at different places, phase transitions, exotic states of matter, and so forth. This is a picture of a liquid crystal. A liquid crystal. These are very useful things that are a basis of many computer displays, for instance. They interact in rich ways with light, as you can see from this picture. The theoretical framework that we use to describe how liquid crystals behave, how they respond to different light and to other things, and to design them, tell people which kind of chemicals they should mix together and in what proportions and what fields they should apply. We use these tools of field theory, and if we want to imagine new things, we can do that too by having the appropriate quasi-worlds. So this is this is how you, as a cartoon version of how you make a liquid crystal, just to show that it's a state sort of in between solids and crystals that many kinds of materials show in a range of temperatures. And you can anticipate and calculate and predict their properties and find useful ones by knowing the shapes of the molecules and using the techniques of field theory to seeing how they fit together. So, and some of them, as a function of temperature, they can have radically different properties. And all of these go into different kinds of displays. So, though there's some of the, by now, classic applications of these ideas of quasi-particles and quasi-worlds, now let me quickly move to two of today's frontiers. One is Anions. These are quasi-particles, so they're things that exist inside materials, and they are a remarkably new kind of particle that has memory, that has a kind of, no, not just a memory, but a topological memory. So it's kind of a very selective memory and very clever memory, but as you'll see. So let me introduce this by talking about what we need to understand if we're going to understand what the relevant topology is. This is the concept of world lines and the concept of braids. Oops. Sorry. So world lines are the following idea. We want to visualize the paths of particles through space as a function of time. So we take space as in a familiar way, picturing space, and then we add time as an extra dimension, say vertical. Okay. Then if we want to see how a particle is moving, to keep track of its motion, we, at each time, trace out where it is. And if you think about it, that'll make a line. That's called a world line going up. Okay, so those are world lines. And if you have several particles, they make a mess of world lines. They can make this kind of spaghetti. Or they can make braids. And the technical word for this is braids. when you have world lines that wrap around each other and have non-trivial topology. This, I won't explain exactly why, but it turns out that to have stable braids that won't come undone in a breeze, so you make a design with your hair, then you tie a rubber band at the end, and then it's topologically stable. It won't come undone if you shake your head or go out in the wind or something. You couldn't do that if you didn't use two-dimensional. If you allowed braids to, if you didn't tie the ends, basically, then it would come undone. It would, so it really requires you have two-dimensional space and one dimension of time. So but two dimensions is not so exotic. That's where computer chips live. Two-dimensional quasi-worlds are very easy to produce and imagine. In fact, they're nice and small, so you can access them. So world lines in flat land make braids, and braids can get very complicated. This was already realized and put to use by some of the Mesoamerican and Southern American civilizations in something called Quipu, which was a robust nonverbal language for information storage and communication based on arrays of knots. So knots can be very complicated, and if you have strands of knots, you can have numbers. There are ways of calculating using these knots. And this was very handy, for instance, in the Andes, where you had different tribes that spoke mutually incomprehensible dialects. This was a universal language, and people could send messages from one place. They also didn't have paper. This was a way of sending messages, and it kind of went out of style after Spain had its influence, but still some of the traditions are kept alive, and you can see. You can get even more information, of course, if you use different colors. And that's done too. Now, back to quasiparticles. Anions are particles with the property that their wave function, so this is at a much higher level of abstraction now, but wave functions are things that physicists deal with and can measure. Their wave function keeps track of how their world lines entangle. So if you think about it, that means the memory, the wave function has a memory that we can, if we're clever, we can try to access. So they, not just roughly speaking, but precisely, they memorize the braid that their world lines form, or at least some aspects of the braid. In 1984, specifically by thinking along these lines of quasi-worlds and quasi-particles, I predicted that the stable concentrations of energy, or quasi-particles within certain two-dimensional quasi-worlds, the so-called quantum Hall liquids, would be anions, would have this property. And at the time, I thought it would be a matter of months before this got checked. But it actually took 40 years. But worth waiting for. Here is the paper from June of 2020, which clearly demonstrated this kind of memory effect. What was actually, just to touch base with reality here, this was the experimental setup. You have currents of anions, of predicted anions, quasi-particles that could go from the top here to the bottom where the current is read out in two different ways. The bridges are difficult to scan, are difficult to get across, so you only cross once, you cross the minimal number of times, so there are two basic paths that the particles can follow, either jumping across here or jumping across here, okay? I should have said that these particles always propagate unidirectionally, so they can only go counterclockwise. And I need to be, so they can go this way or that way. And then if there are anions inside, they will make a difference to the behavior of the relative behavior of these currents, because if you think about the current that goes this way, if there's an anion in the middle, the anion will versus the particle that goes that way, that the difference between them encircles the anion once, and that entangles their braids, and so it's predicted that depending on how many anions are in there, the current will have, the contributions to the currents will add up in different ways. Now, since the number of anions is a number, a whole number, what's being predicted is that there should be jumps in the current when one additional anion pops in. And now you're prepared for what I think is one of the most beautiful illustrations to emerge in modern physics. There are the jumps, and the theory predicts their magnitude and basically where they should occur. And so this is very nice, finally. One can also manufacture anions, and this is using the same ideas, but now trying to make them in a more convenient form than these quantum Hall effect systems. And this is still an ongoing pursuit, but there was a certain milestone passed in 2016 when a very small system was using these ideas, showed that if you have basically superconducting loops of current and then superconducting lumps of charge, that pass around each other, they exhibit anion behavior. And that's true. And this line of work has inspired a vision. This is a vision called topological quantum computing. And here's the idea. I told you that braids can get very complicated. That means you can store a lot of information in them, and you can do a lot of parallel processing by winding particles through the net, the mesh, so to speak. So if you do this in a clever way, in the right kind of material, you can do useful computations, and in fact, computations that embody the idea of a quantum computer. So which has some remarkable properties that in some ways are superior to the computers we have today if you could do it on a large enough scale. And the special thing about this way of computing things, which to be sure is quite exotic and almost outlandish, is that a big problem with quantum information and the kind of information you want to exploit in quantum computing is that it's very delicate. So interactions with the outside world can tend to wash it out. However, if the information is topological, then small jiggles like that don't change the topology. Okay? They don't change how many times things have wound around each other. So this kind of quantum information and this kind of computing has very large advantages when it comes to being safe from sources of noise and interference. Very recently, in the last week, Microsoft announced that they've produced anions of a sort that could potentially be used for quantum computing and could potentially be produced on an industrial scale. So this is coming along. Okay. Now let me switch to Axion, my second case study, Axions, which is something that actually is a nice illustration of Steve's generosity. He and I were both working on the same kind of idea at the same time in the mid-70s without knowing it. He was already a very, very distinguished figure, and I was not. But what happened was that Kurt Callan, who was my colleague at Princeton, gave a seminar at Harvard about something completely different, but at dinner or lunch, he got to talking with Steve, and Steve asked what people were doing, and Steve and Kurt described what I was doing, and Steve said, "Oh, that sounds a lot like what I'm doing," and he called me up and asked me about this, about what I was doing. He didn't need to do it. I mean, there are colleagues who, given that information, would as fast as possible write up their results and make sure they got all the credit. But Steve called me up, and we agreed to work in parallel and then publish at the same time, and it was very cordial. I should also say that as a result of that, the world got saved from Higlets. Steve was calling these particles Higlets, which is a ghastly idea. But he wisely agreed to call them Axions, which was what I was calling them. All right. So what are axions about? Well, axions are introduced, and they're still hypothetical. They're introduced to address a serious conceptual problem in the foundations of our understanding of nature in the Standard Model. The Standard Model explains so much that we have very high standards for it. We really wanted to explain everything. Okay, we're forgiving if it can't explain the origin of the universe or the inside of a black hole, but we really expect to understand neutrons, for instance. And there's a phenomenon in neutrons that's extremely annoying from that perspective. That is, we're familiar with the idea that spinning objects that can internally contain charge can produce magnetic fields. I mean, the Earth does that. So, and that's called the magnetic dipole moment, because it produces a magnetic field with a certain characteristic form that's aligned with the spin. Why not an electric field? Well, in fact, general principles don't forbid it. However, there's an approximate symmetry that could forbid it, called time reversal symmetry, because if you imagine an electric dipole moment, that's a correlation of spin with an electric field. If you reverse the direction of time, the spin changes, but the electric field doesn't. So time reverse. If time, if there were a non-zero such correlation, it would violate the principle of time reversal. It would look different when you reverse the direction of time. But this symmetry is accurate in this application to roughly 10 billion times the accuracy that we can understand within the standard model. So something is missing in our understanding, we think. And that's what axions are meant to address. But it turns out to be, although that might seem like a very recondite little problem, it turns out to have extremely profound and maybe fertile implications. So the way to think about how this arises in the context of quasi-particles and quasi-worlds, and the idea that space is a material, is that if space is a material, its properties can change in time. So what you might think are constants of nature that are embedded in the laws could actually be just properties of the material that we happen to live in, and maybe could change. So here's the picture that emerges on more detailed implementation of these ideas. You have well, this should be a field, but I'm representing it as particles. So you have to think of it as particles that are all over the place, rolling down from arbitrary conditions in the early universe, down, 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 and if you have arranged things right with appropriate symmetry, and it's not ugly to do, then they will automatically, to minimize their energy, settle down to a place, a value, filling the universe where this neutron dipole moment vanishes with sufficient accuracy. So it's a theory of evolution of what otherwise would be a constant of nature. And, well, the magnitude of this is called a condensate, and the axion is actually the, come on. Oh, yeah. The axion is actually the oscillations in the soft direction, in this direction. That's relatively shallow. Yeah, and this is how it got its name. I was inspired by a laundry detergent. That's a story for another time. Anyway, little did we suspect at the beginning that there was another problem that seeming to come from a completely different source that this circle of ideas could very well address. This is the so-called dark matter problem. There's a form of mass in the universe. There are many, many different kinds of evidence for this. Mass in the universe that's very, very weakly interacting with ordinary matter, cannot be identified with anything that we can make out of the materials we know, but looks very much like a particle. And in fact, it looks very much like the predicted axion. So we'd like to know if that's what it is. Oh, here you see dark matter causing excess gravitational bending of light when you look at distant galaxies, for instance. So, just in case you doubt my credibility, many physicists have put enormous effort into trying to rule in or rule out this hypothesis of axions, and in particular axions as dark matter. So there are many, many experiments. The axion theory is, unfortunately, it's a one-parameter theory. There's an important parameter we don't know the value of, so it goes in here. I should say Professor Fischler was influential in having us realize that there was this parameter. In fact, F is for Fischler here somewhere. Yeah, right? There. Okay. So there are many, many experiments. People have put a lot of effort into this. And one of the experiments, just to show how far people propose to go, is this so-called EAXO experiment. And you can see the scale of it. This is a rather tall Scandinavian physicist. And this is the proposed thing, which is supposed to look at the sun, be full of magnetic field, and in the magnetic field, axions might convert into photons. Even though it's gigantic, it's meant to move, because you always want to be pointing at the sun. So, people are going to great lengths to look for axions. Let me show you, however, how a strategy that some of us have been following recently that looks extremely promising, based really on these thoughts about having quasi-worlds, designing quasi-worlds in which things behave different. So first of all, some bad news. People who've worked out so this is a one-parameter theory, but only for one value of the parameter would it actually, in the early universe, make the dark matter. I'm oversimplifying a bit here, but for present purposes, let's say that. And there's the prediction for the mass, and these estimates have gotten more and more refined over the years, and now there's a prediction. So this should be a mass of 40 to 100 microelectron volts. It's a very, very light particle by particle physics standards. We usually, instead of micro, we usually at least have 1 over micro, million electron volts or billion electron volts, megavolts or gigavolts, but this is on the other side, and that corresponds using the relationship between mass and energy and frequency to which is what you actually detect is at the end of the day the frequency of some light that the axion converts into, to a range from 10 to 45 gigahertz. And on this plot, it's there. And you see the experiments are either not in the right place or not sensitive enough, unfortunately. However, we can try to design a quasi-world where quasi-photons behave like axions. Okay, we can't really modify the properties of axions very much. They're very weakly interacting particles. But we can change photons so that they become the same as axions. The quasi-photons, I should say, inside an appropriate material could mix with, or the jargon is resonate with photons. So they have all the same properties of photons. And given long enough, they would oscillate from one to the other. The material involved is something called a wire metamaterial. It's an array of wires, and you can change the resonant frequency by changing the spacing of the wires, so it's possible to scan. And this is a prototype design. And this is a prototype. Things are moving very fast. And it works. It works, in fact, much better than the original estimates that were contained in that theoretical paper. And so what we think we can do, well, this is more or less what the experiment is going to look like, but actually we've gotten our hands on a much bigger magnet, and so we might be able to skip this stage of Pathfinder. And we think we think we can do this conservatively and hope to do even better. And this was that sweet spot of where the mass is expected to be. So it's a very interesting and promising situation. Okay, so those are two case studies where I think, well, I know because I was involved, the concept of quasi-worlds has been extremely fruitful, and we'll see exactly how fruitful in the future, but it's certainly been interesting and driven research in physics. Now I'd like to very briefly wind up by looking ahead to the future. There's no reason you have to stop at quasi-particles and quasi-worlds. You can talk about quasi-cells, quasi-organisms, and quasi-universes, quasi-multiverses, I should say, not just quasi-worlds, but quasi-multiverses. So let's see what that is. Quasi-cells and quasi-organisms. Well, biology has a very, very impressive trick that it can develop from puny cells, tiny, tiny microscopic egg cells into impressive organisms. And it does that by self-replication with variation. Oh, sorry, I got it. I blew the punchline, but okay. Does physics have anything like that? Do the tools we've developed in physics have potential application here? And I claim very much yes. If you look at, for instance, the development of cosmic ray air showers, but this is not the only case, what you have is building up from an initial seed a kind of chain reaction. Well, chain reaction is another example, by the way, where the initial very energetic particle collides with others, and more particles come out, and then each of those initiates more development, and you have a quasi-development of an extensive cosmic ray shower. Or you can think of it as a kind of quasi-evolution where you start with a few individuals and they reproduce to create a big population. Or you could think it could be a quasi-pandemic too, if you want to be up to date. But what all these things have in common, so if we want to think about universal theories and exploiting these ideas, physicists like to simplify and then universify. What all these things have in common, which is, I think, undervalued and underrepresented in current day physics and engineering, is the theme of self-replication with variation. This is a very, very powerful theme. If you can go from one unit to others that have also the capability of going from one to others and developing whole populations that can cooperate. That's, I believe, the engineering of the future. To do it in a way that's flexible and powerful, if you want to think about doing things like terraforming planets or sending messengers out into the galaxy, you need the individual units to be pretty powerful. Not as powerful or complex as a biological cell, but capable of reading instructions, doing construction, and reproducing themselves. And already in the 1950s, John von Neumann made some conceptual designs along these lines. And I think it's high time that we take up the challenge. And then you could have them make a quasi-organism. What about the quasi-multiverse, which is my final topic? The multiverse is something that figured very prominently in some of Steve's work. And some physicists react very negatively to the multiverse. But let me show you why you shouldn't. At least, so this is the conjectural multiverse, stuff that's very far away, that behaves in very different ways than what we see here. And the weakness of the theory is that it might be so far away that you can't see it. At least you'll have to wait many, many, many billions of years before it might become visible, or maybe never. So it's conjectural and difficult for some people to accept. But if we have theoretical control, we can draw the consequences of theories, even though they're hard to check. But if they're intellectually consistent and rigorous, we can still have some confidence. In any case, here's a multiverse. If you think of different materials as worlds in their own, as we've been doing, thinking about them as things with their own coherent kind of behavior and descriptions and as effective field theories, when you have lots of them together, that's exactly a quasi-multiverse. And they're produced by natural processes. In fact, it's hard to avoid a quasi-multiverse if you pick up a random thing produced by nature. And sometimes a quasi-multi-universe can even be useful. Okay? This transistor, the sort of epitome of modern technology, is a combination of three universes, three quasi-worlds with different properties, one dominated by these holes, that's the N, and I'm sorry, that's one dominated by quasi-electrons, that's the N region, and one dominated by holes that introduced chemically, that's the P region, and it can make something very, very useful. Physicists, I've tried to do this systematically in recent years, dream up quasi-worlds, and then think about how they interface with each other. Think about how you can try to make useful quasi-multiverses. Okay. So with that thought, I will conclude, and thank you for your attention. Okay.
Thanks. So hi, my name is Sharon Wood, and I'm the provost here at UT Austin. And it is my great pleasure to first off be invited to attend this event, but also to be able to present the first medal for the Steve Weinberg Memorial Lecture. I did want to make a few comments before I actually present the medal. And first is, all of you in the audience can talk more about Steve Weinberg as the brilliant scientist. But I think he had an impact on everyone here at UT. He spent 4 decades of his life here. He talked a lot about natural beauty, and he really helped to create ties across campus. I think also he used his status as a scientist to talk about some of the greatest challenges facing society. And he looked at nuclear proliferation, and he really made a statement there. And I think we have all had the advantage of not having to face the challenges of the Cold War right in our face for many years, but it's there now. And so I think we should take the lesson from what Steve has shown us and use our voice as scientists to help make statements. So it also now is my great pleasure to present on behalf of UT Austin, to present Frank Wilczek with the memorial medal. So I will present this to you here. I won't attempt to put it on. I will get your glasses instead. And there's absolutely no doubt that if Steve were here today, he would have also chosen Dr. Wilczek to present this first lecture. So we're going to transition now to questions and answers for Dr. Wilczek. If you're in the audience, There are 2 microphones, so we ask that you move forward to those microphones. If you are attending virtually, then Dr. Laguna will be checking those and reading those questions to Dr. Wilczek. So thank you again.
I've been delegated to read the online questions while Dr. Laguna will handle the in-person questions. So while people come up to the microphones to ask questions, I'll quickly read off some of the questions online. So one question from Eloini Mohammed is, what is your comment, Dr. Wilczek, about quasi-particles in the context of topological states of materials?
Well, topological states of materials are very interesting quasi-worlds. And the quasi-particles within those can have some very special features. In fact, I think the anions in the quantum Hall effect are maybe the epitome of that. So yes, the topology has become an extremely important theme in modern physics, and the quasi-particles that have this kind of topological character, where their interactions depend on the topology either of the particles themselves or of their world lines, have really been the focus of a very large proportion of work in condensed matter physics the last few years.
Thank you for a beautiful and inspiring lecture.
Thank you.
I wanted to ask about not a word, but a prefix, quasi. I wanted to ask you to expand a little bit on what it means to you. It seems at first simply to indicate a lack of commitment. A quasi-particle is not quite a particle, and yet these quasi-particles have quite taken over the world and are more real than the realest things.
Right.
So what does this prefix mean to you?
It's a historical artifact, but I think a useful one. Because in the early days, people thought of fundamental particles as one thing, and their modifications or things that emerged only within materials as another, and but realized that the excitations within materials had a particle-like character, as in the case of the phonon, but also. So for reasons I don't know, it was long before my time, people talked about these things as quasi-particles, but I think basically it was because they thought of them as second-class particles, not the real thing that exist in empty space. But now that we have a more sophisticated knowledge of, first of all, how beautiful and coherent the ideas of emergent particles in materials can be, and also an increased appreciation of the fact that what we perceive as empty space is not really empty at all, but very much a material, then the quasi is in no way appropriate as a denigration, but it still might be useful as just making a distinction.
So we'll have another question from online. The ubiquitous questioner Anonymous asks, is a positron a quasi-particle?
No, a positron would be considered as a legitimate particle, as long as it's an empty space. Yes. So.
Can I? Okay.
Yes.
So this is from Louise Weinberg. She said, Professor Wilczek, sorry I can't be here in person with you. I want you to know that you are the very physicist that Steve would have chosen himself to give the inaugural lecture.
Oh my gosh.
I've read through his memoirs, and I know how much he admired you and how intrigued he was by the congruence of minds. Congratulations, and thank you so much.
Oh
Louise.
gosh, thank you. Wow. Well, thank you, Louise. I met Louise a couple of times. She didn't remember. She claimed that she never met me, but it's not true. I just didn't make much of an impression. But I met her twice, once in Cambridge, for a long time she and Steve maintained their home in Cambridge long after he left for greener pastures. And once here in Austin. And what I remember, that she was a very, very charming woman, but also that we had a common interest in playing the piano. When I interacted with her in Texas, Steve was very proud to say that she was learning how to play ragtime on the piano, and then she indulged me by listening to my slaughter of some Schubert, and being very restrained. All right. Okay.
We also have a question, I believe, inspired from the early part of your talk, from Jim Moyle. Can the velocity of gravitational waves be measured? Is it the same as the speed of light?
It can be measured because these sources emit not only gravitational radiation, but also radiation of more ordinary kinds. And you can compare their speeds, including light. Now, it's a little bit complicated because they don't necessarily emit all this radiation at the same time. The gravitational radiation tends to get out first. But they're very, very far away. So if the difference in speed were significant, you would definitely see the separation. So you can put strong bounds on the speed of gravitational radiation based on those kinds of observations. And theoretically, it would be very, very, very surprising if all the fundamental interactions didn't propagate at the speed of light, because the speed of light is not its importance in physics. It's not that it's the speed of light. It's that it's what appears in Lorentz transformations that are the basic ingredients for mixing space and time, and that applies to everybody. Yeah.
I had a question about your idea of the quasi-organisms.
Yes.
That for evolution you need to have replication with variation.
Yes.
But you also need selection, and you need immortality.
You need what?
Immortality. That the individuals don't necessarily survive, but the generations do.
Yeah.
That you have enough generations that you can really see the new forms developing. And
well,
are there things in physics that
cosmic ray shower is just like that? Right.
Well, how many generations do you get in the cosmic ray shower?
What's that?
How many generations do you get in it?
Well, it depends on the initial energy, but you get many, many. And the energy within a branch generally gets smaller and smaller, and in a sense whiffs out or dies, but you produce many, many individuals by the time it hits Earth. So I think those features are, yes, I mean, to have rich biology and evolution by natural selection, you have to have lots of individuals, but that's not at all in conflict with these general ideas. That's a feature, I would say, if you had many of these things and they had to compete for resources, and that you could build that in. Yeah. Thanks.
Could you comment a bit more about Microsoft's new claim to create non-abelian anions? Because I know it's contentious because they had to retract their previous claim, right? So
I can't. Sorry, I know a lot more, but I'm not allowed to talk about it. There's proprietary information. Let me just say that it's which I don't really know all the details myself. I was shown graphs with not to scale and things like this. But what I can say, I think, which is fair, is that it's extremely impressive. They have really impressive now Majorana modes. Now, so that's a big.
Another question from JD online is, both Steven Weinberg and yourself have worked on grand unified theories. Is there any hope that we will ever observe any evidence for grand unified theories?
Oh, well. You already have. For the fact that neutrinos have a very small but non-zero mass, small compared to other elementary particles, but non-zero was a primary prediction of unified theories. Also, I don't know if you'd call it, well, no, it is a prediction, I'm sorry. So there's a pattern of the particles that are in the standard model that can be explained if you embed them in a larger group, so with more extensive symmetry, and I guess the prediction is that that pattern will continue to hold up, and so far it's held up by no more particles being discovered, but that it held up. So you didn't find any oddball things that weren't consistent with that framework, and then so I would say the other. Oh, and then there's the most impressive. Quantitative evidence, which is very impressive, is something that Steve also pioneered, actually, using renormalization group, which is what I got the Nobel Prize for, on the different coupling constants that appear in the standard model. They certainly seem to converge as you go towards shorter distances, where you sort of would expect to be stripping away the complications. They seem to be converging towards a common value. Okay. Now, to get really precise agreements, you would need low energy supersymmetry. So far, that hasn't shown up, but there's still hope. And then the other big prediction, I would say, of unification is proton instability. And that unfortunately has not shown up yet, but people should definitely keep trying. Okay, it's just.
Thank you.
Yes.
Hi. You said that it's very challenging to detect the signal from axion particles.
Yes.
Do you think it's possible to amplify it through the axionic quasi-particles in topological materials?
Well, that has been suggested, and but so far, I think the wire metamaterials look more promising. That could change, but at present, the wire metamaterials are much more developed.
All right. Well, I want to thank you, all of you, for attending the lecture, and the 600 people that are doing it online. And I want to thank Willie Fischler for his kind words and Provost Sharon Wood. And please, let's acknowledge again.